In this lecture, we're going to try to set up Riemann sum to try to find a volume of a solid three-dimensional object. The method we use is called cross-section. With the method, we're going to develop disk formula and washer formula for some special solid. Let's first get to know how we, in general, come up with a Riemann sum for volume of solid. Suppose we place this like a potato along number 9, it's the x-axis. Say the x-axis come out at the location B. Say this end entering at location A. All right. The idea is we slice this solid perpendicular to x-axis. Make a cut, infinite many cuts between A and B. Say this is a representative one slice. With thickness dx. Alright, so the idea is if we can calculate or estimate volume of one slice called the dV, then we add from this end to this end, so all those volumes of slices would be added up, then total volume would be the integral a to b dV. So the key is to come up with the volume increment formula, which say the volume of one slice. Now, how do we find the volume of one slice? Well, let's place it here. Not necessarily a perfect circle, just a slice of potato or tomato or potato, whatever. Right. So now we know the thickness is dx. It's taken out from here. The dx usually thickness is very, very small. So roughly speaking, we can think of this as a cylinder, meaning the top face and the bottom face are almost identical. Thus, this would be considered as a cylinder. Once it's regarded as a cylinder, all we need to do is to find the area expression of the cross-sectional surface here. That's why this method is called cross-sectional approach. So if we find A of x, which would be the same area here. Now this area, as you can see, is a function of the location where we pick up the slice. For example, if a slice is picked up toward this end, it's going to be smaller. It varies, so it's a function of the location. We basically just say location, whatever location it is, say x here or x here. Now dx is so small, so it doesn't matter which point we pick up as the x to figure out the cross-sectional area. But anyway, this is how we come up with the name, the method of cross-section. Now if we find A of x, then multiply by dx. This is like the area of the base times the height volume of this cylinder, which is the thin slice taken out from this solid. So this is how we come up with the definite integral But with the details, we would really go through the old Riemann-Sum approach. Say at this x of I, we calculate a of x of I if we can, and then do the delta x thickness, of course, before we would do b minus a over n with n slice with the I from 1 to n, let's send n to infinity, and that's how we come up with actually the definite integral notation. All right, so this is how we set up Riemann-Sum to come up with a definite integral for volume of a solid. It's nice, but the problem is usually if this is irregular, it's just any arbitrary solid, it's impossible to find a of x. That's the only problem. Well, in this section though, we're going to use the method to consider special solid. It's called the solid of revolution. Let's consider a function with the graph showing here. Suppose the region under the graph above x-axis and between A and B is revolved around a line, say x-axis. Then we would see a solid called volume of revolution. In this case, AB possible to find expression for the cross-sectional area. Let's see. Again, we take a slice, we slice and take thin piece. Again, place it here. Now this time, it's a perfect circle. So the A of x would be pi r squared. R be the radius of this circle. Then our total volume would be the sum of all these dv's. This time, notice our dv would be ax times dx. dx is the thickness, or from the original graph will be there. All right. So the dv now pi r squared dx. So it's the same cross-sectional method for this kind of a special solid. Since the slice we take out from the solid is a disk, this formula is also called disk formula. It's called disk formula. And the radius r here, we can see would be the distance here. dx is the width of this slice, thickness of the slice. All right. Now the thickness could be dx, could be dy, depending on which way the region is revolved. We'll get to that. We'll explain how we get, when we get the dx, when we get the dy. All right, so this is our disk formula. Now, when we actually work on problem like this, we don't start by rotating the whole thing. Let's see a different approach to get the same formula. It's the same problem. Okay, we want to revolve this region. Okay, around again x-axis. Now this time we're going to slice the region first. Let's see. Slice the region into many slices and rotate each slice. Each strip. You can see revolution of this strip would generate the same disk as we got here. So the order is different, but the result is the same. So once we got a representation for volume of this slice, which is the same, pi r squared dx. This is again the same r. And this is again the same thickness dx. Then we add all those disks up, volumes of these disks up. So we basically just integrate. So be A to B, add all those things up. Same formula as we would get here. All right. Now, before we get to a more complicated solid of revolution, I want to spend a little time explaining why sometimes we have dx, why sometimes we have dy, and how we know whether we should get the dx or we should get dy. Let's see another region. Say like this. Revolved around, this time, y-axis. So we pick up a strip this time, revolve. We have again a disk. All right. So this time RDV will look like pi r squared. Say this is r. Radius. Pi r squared would be cross-sectional area times thickness. Now thickness, if you look at the graph, is measured by the y increment here. Therefore, it's multiplied by dy. Then with the same idea, the total volume will be the sum of those guys starting from this to this, because our disk this time will stack up, from the bottom to top. So be whatever called C, called D. So be C to D pi r squared dy. Again, it's a disk, but you see dy here. Now, so we get dy this time. You ask, well, in general, how do we know whether we get dx or dy? It's very important. It's not just, it's the right thing you have. It also indicates the variable you would have. Okay, if the thickness, for example, like in this case is dy, then everything must be expressed in terms of y. Well, this kind of situation, your thickness is dx, everything here or similarly here would be expressed in terms of x. So that'd be like the integration variable we use, the right variable, x variable here, and the y variable here in this case, right? So how do we know whether we should have dx dy? Well, there are two ways to know it. One, just memorize it. As you can tell here too, when you have a horizontal strip, it's dy. When you have a vertical strip, It's dx. You say, I don't want to memorize it. You don't need to, because given a region, no matter how you rotate it, around the horizontal line, vertical line, you always have to pick up a strip. Say you pick up a vertical strip. In the vertical strip, see, in this case, if you extend it, it would intersect with the x-axis, and that says dx. All right. Or if instead you pick up a horizontal strip, extend it, you would hit the y-axis, so it's a dy. Now, of course, there are cases you don't even need to extend, like here. It already intersected the strip, already intersected with the y-axis. Of course, it's dy. If instead the strip intersect with x-axis already, of course, it's a dx. Okay. So anyway, our disk formula, but remember, it could be dy here, depending on the strip you pick up. All right. Once you find this, all you have to do just to add, set up an integral. Just put in the integral. So I want you to become familiar with this, not the final integral, because once you get this, then you get that. In different situations, your final integral may look different, but you always use this disk formula. Again, could be dy here. All right. Before we get to examples, concrete problem, I want to show you another more general case. Let's see. This time, I'm going to revolve a region between two graphs, f of x, g of x, around, say, again, x-axis. Okay. So what happens is, this time the solid would look like, just say, the three-dimensional solid first, then we come up with a strategy to come up with a more easily used formula. So it would look like this. It's almost like a pipe, right, with a hole going through, that kind of solid. All right. But this is just to show you what the solid is like. Now, how we do it is, we would have to pick up a strip and see the revolution of that. It's a little messy here. Well, let's just see. See this, the revolution. Of one strip only. So idea is, we find the volume of this one slice, which we call the washer. Think of this slice of pineapple with the middle part removed. Then we add them up. That would give us the total volume. But then the key is to find the volume of one slice. Now, how do we find the volume of one slice? Let's just focus on revolution of one slice. So let's do the graph again down here. So this time, we're going to just start with the slice. Just revolve. Now we have the same washer shaped slice. Of course, the idea is, if we could find volume for one slice. Then we add up from A to B. So how do we find the volume for this one washer? Well, we regard this washer as a smaller disk removed from larger disk. This way, the difference of these two would be the volume of the washer, right? Now, the question is, what's the volume of the larger disk? Well, we had our disk formula right here. It's pi r squared dx. By the way, it's dx. We still need to determine the variable to use or thickness of the slice. In this case, extend that. You have dx, right? So the key is to find the radius. For now, let's look at the graph, and we see this would be the radius. Let me call it as r out. I'll explain why it's called r out. Let's just call it r out. So this radius called r out, that be the radius of the larger circle or outer circle. That's why it's called r out. All right. Volume of this larger disk would be pi r out squared dx. While volume of the smaller disk, again disk, so we're going to use the same formula, but the radius is shorter, called r in, because that's the radius of the inner circle. All right, based on the formula, we again have it as r in squared dx. So the difference of these two would give us volume of the washer. So subtract this from that with the pi factor out, dx factor out, put it back too. So we have this formula for the volume of the washer. This is what we called washer formula. All right. Now in this formula, well, because we pick up vertical strip, this was the strip that was revolved. Okay. We use a dx here. Everything in the expression must be in x. X is the variable of integration when we add everything up. If instead a horizontal strip is picked up to generate a washer, then you know it's going to be dy here. All right. So this is how we come up with our washer formula and disk formula based on the method of cross-section, which is based on the Riemann-Son idea. Now, there's one more thing we need to talk about, very important, very simple thing too, before we get to examples. Notice in complicated problem like this or simpler disk related problem, we need to figure out the distance, like inner radius r in, outer radius r out from the graph. From the graph, we may say horizontal distance, we may say vertical distance. So there are all kinds of distances we need to identify from the graph. Graph is important. We'll get to that. But anyway, let's talk about the distance. So there are two types of distances everywhere you see in the picture. So how do we in general figure out, say, vertical distance? Simple. Vertical distance be the y value or y expression above minus y value or y expression below. Common sense, right? While horizontal distance, sometimes we need to figure out, would be the x expression or x value at the right end minus the x at the left. Again, common sense. Very simple, but extremely important. This formula, of course, shows the right one to use, but also it gives us a hint as what kind of expression we can plug in actual problem. If we don't pay attention to what we can plug in, we can be in big trouble. We can easily get confused. Alright, I'll get back to those formulas. Very simple formula, but extremely important. When we get to example. Alright, let's see example. Example 1. Find volume of the solid that's generated by rotating it around x-axis. The region bounded by the graph of y equal to x minus x to the third power shown here, and y equal to 0. Well, what we're saying is this region, which is bounded by graph here and graph here, is rotated around x-axis. So we get solid revolution, we need to find the volume, so on, right? So it's very important to graph all these functions, equations involved. Without the graph, there's nothing you can do. So now we see the region, pick up strip. Vertical strip, immediately dx. Just write it down before we forget. So everything will be expressed in terms of x. All right. Now rotate. So pick up strip and rotate as instructed around the x-axis. So rotate. How do you rotate? How do you rotate the strip so you get like a decent picture? Very simple. You don't have to be an artist. Rotate always ends. So rotate, let's say, for example, top end around the line, you have a circle, right? With the line going through, with axis going through the middle. Then you rotate the bottom end. Well, this time the bottom end is on x-axis, so it's not really moving around. It's just spinning at the same, spot. All right. So what we're saying is the revolution of this strip this time is a disk. So disk formula, pi r squared, we already determined its dx. Right? And the radius r, as we see from the graph, only from the graph. There. Okay, so before we add all those things up from A to B, clearly it's from 0 to 1 in this problem. We need to figure out the expression for R. Now, how do we figure out the correct expression for R? We rely on the graph to see, first of all, where it is, what's involved, what kind of distance it is. So there's a lot of things, pretty much everything besides this formula we know. everything we do are based on the graph. So the graph is very, very, very important. Anyway, from the graph, we see the distance we're trying to figure out this time is vertical distance. Vertical distance, if you recall here, is YA minus YB. Write it down. YA, YB. Very, very important. Okay, so when you look at the strip, YA would mean the Y value or Y expression above. YB would mean the Y value or Y expression below. It's called YB, right? Let's see what A is. YA, as we see, is a point on the graph of this function, which is represented by this equation. So we know it has everything to do with this equation. One thing we have to pay attention to is we are looking for YA, meaning Y value or Y expression. So it has to be in the form of a Y equal to. Now, the correct equation we identified here happens to be in the right form, in the form of a Y equal to. So we directly plug in. Sometimes you find that the correct expression is not in the right form. If you're not thinking, right, just plug in, you could be wrong. Okay, so we identified the equation. We also notice it is in the right form, Y equal to, because this is a Y, has to be Y equal to, Y equal to, right? Now YB. YB is the Y value or Y expression. Sometimes you're given Y value, sometimes you're given Y expression. Like up here, it's a Y expression. Down here, let's see, it's Y value. Y value is 0. So we plug in 0 for YB. So this would give us the expression for radius, which is, this case, a vertical distance. And we plug in. So our dV is pi, this is R. 0, you can just drop it, the square dx. Alright, and check, everything is in x, so we're in good shape. Let's simplify, just square this out, do the algebra, right? X squared minus 2, x times x to the x to the 4th, plus x to 6 dx. So this is volume of one disk, representative. Pick it up at the location x. Now we add all those disks up, starting from 0, cross the interval, stop at 1. So the total volume will be 0 to 1, sum of all those guys. Now the integration involved is pretty trivial. There's a pi you pour out. Antiderivative of that is based on this simple integration formula. Integral of power. It's 1 over n plus 1 x to n plus 1. There's no integral sign anymore. Alright? Now this is definitely integral, so we don't need the plus c. It would get cancelled out anyway. So x to the third power n equal to 2, x to the second power n equal to 2, so it's 1 over 3 x to the third power. And here 2 is constant, copy it down. 4, n equal to 4 is 1 over 5, fifth power, 1 over 7, seventh power, basically, antiderivative or integral. And there's a 0, there's a 1. You plug in 1 for x, then plug in 0 for x, subtract. So 1 plug in, well, power of 1, any power of 1 is 1. So we basically have 1/3, 2 over 5, 1 over 7. This is what we get when 1 is plugged in for x. Now 0 plug in, it's 0 everywhere, so it's just pi times 0 or 0. So this would be our answer with a calculator or with a simple calculation. We can figure out this by hand too, but that's not important. All right, so this is how we find the volume of a solid that's revolved around the line by region enclosed by the graph here, and y equal to 0, which is x-axis. We start by pick up a strip, revolve. Now revolution of a strip is a washer, then we use the washer formula. And of course the dx, because we pick up a vertical strip, so variable is x. Next, let's see this example. This time I'm going to find the volume of a solid that's generated by rotating around the line x equal to 3, the region bounded by graphs of y equal to x squared, x equal to y squared. Now x equal to y squared is this, y equal to x squared is this, so it's revolved around x equal to 3. Okay, now we learned this is a disk method, washer method, so whatever strip we pick up, this strip has to generate either a disk or a washer. Okay, well in this case we have to pick up horizontal strip. You'll see. Okay, horizontal strip. Now since we pick up horizontal strip, immediately extend it, we find the dy. Very important. So this not just gives us the correct thickness, it also indicates the variable we're going to use. Extremely important. All right, so let's do some artwork, which is not bad. We're going to revolve this strip around x equal to 3. Now always revolve ends. The right end, revolve it, just pretty much get a circle with 9x equal to 3 going through the middle. Revolve this end around the same line, we get a larger circle, right? So more or less we see a washer. Now washer formula is pi times r out squared minus r in squared times the thickness. So you can write this a pi r out r in dy here. Okay, so well, what's r out? What's r in? We have to look at the graph. Okay, our region. This is our region. Okay, shade the region, so it's useful. Okay, so look at the graph. R out is the radius of the outer circle. This is the outer circle, so radius is this. This is R out, red. Let's figure out that first, and then we talk about R in. Look at the graph. R out, well, first of all, is horizontal distance. It's a distance. It's a horizontal distance. For horizontal distance, the formula we use is xr minus xl, horizontal distance. So copy that. Yeah. get all those details so you know exactly what to have and how to figure out each involved quantity. Okay, so again from the graph, only from the graph, we see XR is the X expression or X value at this end. What is that? Well, that's at X equal to 3. So we plug in 3 for that. X equal to 3. Alright. XL is the X value or X expression at the left end. And we see from the graph, again, only from the graph here. It's this location, which is a point on the graph of this equation. Right? Let me just show you and see this portion. All right. First of all, we identify the equation x equal to y squared. Second of all, well, we see this is also in the right form, x equal to form, because we are looking for x equal to here. So that's convenient. So just directly plug in. And also won't hurt to just kind of check. Yeah, we have this expression y, which is what we're supposed to have, right? We identified the y as variable earlier. Well, this is R out. So plug in. Be 3 minus y squared minus, now let's try to figure out R in. Where is R in? Alright, from the graph we can tell R in is the inner radius in blue here. And it's again a horizontal distance. Again, we have XR minus XL for horizontal distance. This XR and XL are different than those. So these are for this inner radius. Those are for the outer radius. As you can see here, the XR this time is here. XL is here for different line segment. Okay, so we just need to figure out each. Okay, let's start with the right end. Right end, the x value is again 3 from the graph. Left end this time. Left end, the point is on the graph of y equal to x squared. That represents this graph. Alright, that's the right equation. But that's not the right form. We cannot just say, oh yeah, y equal to x squared, let's plug in x squared. That'd be wrong. Look at it here. We are looking for x equal to, and this is the y equal to. Well, algebraically, what it means is we just need to solve this for x. Just express it in the right form, x equal to whatever form. So the correct expression we're plugging is square y, right? So it's very important to make sure you plug in the right form. Now, how you do that? Well, one thing you do is basically just go by those simple formulas, x minus x or y minus y in different situations that we'll run into later on in this course. But you can see here, it's not enough to just identify the correct expression that represents the graph where you find your point, XL, also the right form. Okay, so this is the expression for R in. It's in terms of y. That looks correct. So plug in 3 minus 4R in square dy. Alright, we can simplify before we add everything up. Okay, so pi, square this out, just all, it's going to be all powers. it's going to be 9 minus 6 y squared plus y to the 4th power minus 9 minus, it become plus 6 square y plus will become minus y dy. The 9 and the 9 cancel each other. Anyway, so this would be the expression for the volume of one washer. Total volume would be the sum of volumes of the washers, starting from the y location here, right? Those slices, those strips, then up to this location. Now, geometrically, we can see this is where x to the y square and the y equal to x square intersect with each other. So how we find the coordinates of intersection? We said that y equal to y or x equal to y, x, but keep in mind you're looking for the y value up here, whatever answer you're going to get. So let's do simple math. Say we set the x equal to x. This way we get the solution as a y value right away. So this green thing is x to the y square. Well, the red thing is y equal to x squared, but I solve it as x equal to square y. So let's set this two x expressions to equal to each other. So I get y squared equal to square y. How do we solve that? We square both sides and move y over, factor out. Then there's one solution, y equal to 0, another solution, y equal to 1. You set this equal to 0. Move 1 over, take a cubic root, so it's 1. Anyway, find the two solutions. So y equal to 0, y equal to 1, and it makes sense, right? Y equal to 0 here, intersection, that's actually another intersection, right? Y equal to 0, y equal to 1. That's why our definite will go from 0 to 1 pi of this, where 9 and 9 cancel out each other. So it's negative 6y squared plus y to the 4th power plus 6 times y to half power, just square root of y, minus y dy. Because again, it's a simple integral because they're all power, so there's no technique or anything involved. Simple formula. So copy on the pi, you find the antiderivative. Negative 6 over 3 y to the 3rd power, 1 over 4 plus 1 is 5, y to the 5th power, 6 over 1 half plus 1, 3 halves, 1 over 2 y squared. Antiderivative. Now you plug in 1, you plug in 0. Okay, then your answer will be, just say plug in 1 for y first. This is actually negative 2 times 1. This is 1/5 times 1. Now what's this? This is 3 over 2. 3 over 2 flip. So it's 6 times 2 over 3. 12 over 3 is 4. So 4 times 1. So it's 4 here. And it's 1/2 minus all 0. Well, again, with the calculator, it should be pretty easy to figure out what this is. And this will be our final answer. The volume of the solid. Alright, so again, how we work on this problem was we approach this problem by picking up a strip to revolve. Horizontal strip, other times a vertical strip. Just make sure the revolution of the strip, pick it up, is going to generate either a disc or a washer, otherwise we won't be able to do it. All right, so anyway, this case we had to pick up a horizontal strip to generate the washer. Let me just quickly show you what would happen if you pick up a round strip. You can always change your mind if it's not getting what you were looking for. X equal to 3, just simply say pick up for this problem a vertical strip and try. Just say, okay, we're going to revolve around this line. I'm going to revolve the bottom end around this line. Would generate, as big a circle, but this is a strip, so then we see almost like a cylinder, right? This is not going to be a disc or washer, so this would not work out. That's fine. You just choose horizontal instead of vertical. Okay. So now with the horizontal, just quick review. Revolve ends, get a smaller circle. Revolve this end, get a larger circle. Yeah, it looks like a washer. So you can use the washer method, and because the horizontal strip was picked up, you can use dy. The rest is to try to figure out correct expression for the radiuses involved. Okay, outer radius, inner radius, where are they? What are they? How are we going to figure out? All based on the graph. Okay, R out is this distance, so it's a horizontal. You go by x minus x. If it's vertical, it's y minus y. All right. So extremely important, okay? Sometimes you have both type of distance in one problem. So doesn't matter, what the situation. You just follow the rules, use the right formula. So when you use the formula, so whether it's x minus x or y minus y, it shows you, okay, the kind of form you can plug in. It has to be x equal to number or x equal to some expression to plug in. All right. In particular, when we were trying to find out xl for the inner radius, the blue indicated the blue here, inner radius here. The equation was y equal to x squared. That is correct, but it's not in the right form because we're looking for x equal to, right? So the x equal to, well, the right form can be obtained by simply simple algebra, solving this for x. Take a square root of both sides, so we find it in the right form. Those two equations are basically equivalent. It's just this is in the right form in this problem. This is not. All right. So it's extremely important that you come with the correct graph. From the graph, you can tell horizontal, vertical. Where is the x right? Where is the x left? So on. All right. So all those volume problems, you start with the graph. Even the area problems before in calculus 1, you have to see the region. You have to have a graph to see the region. So it's not surprising now that the things are getting more complicated. You get the graph to get everything done. Without the graph, well, nothing can be done correctly. All right, so this is the disc method and washer method. Now, from these two examples, you see we didn't know which formula we would use. We simply just pick up a strip and revolve. If the revolution of a strip is a disc, we use a disc formula. Revolution of a strip is washer, we use a washer formula. Just go from there. All right. But just all those formulas are based on this method of cross-section, which is obtained by setting Riemann sum. The same idea we've been applying to do various application problems. Okay.